we do a lot of work in this space, I suppose, and my role within Orica is having a bit of background in mining, helping the business to build and develop new technology that is sort of meaningful for the industry. So we've got a pretty good history at times of developing new tech that isn't necessarily something that the industry wants. So this is a project that stemmed from the industry. There was a lot of feedback over many years from the industry that we need to do something about the exposure to development charging personnel, and that's where Avatel stemmed from. So it's all around safer work at the face. As a bit of context for why this is important, we also spoke a bit this morning around trends in mining and what's changing. What we're seeing around the globe is that mining's transitioning to underground. Underground mines are getting deeper, they're getting bigger. Part of the reason for that is that we've depleted a lot of the shallow, high-grade ore bodies, and we're having to go and chase grade at depth. A lot of mining approvals are very difficult around the world now, of course, so particularly in, say, North America, where it can take 10 years now to get approval for a surface mining operation, and it's only a couple to get an underground mining through and into operation. And then, of course, as we've evolved and innovated as an industry, new equipment, new techniques, new processes, it's improving the economics of underground mining as well, so it's allowing us to go and chase lower grade ore bodies at depth. But it comes at a bit of a cost, and there's some impacts to that. We're seeing increases in seismicity and reduced predictability and geotechnical behaviour, particularly where we're seeing block caving operations with huge stress footprints and big excavations being made. It's difficult to maintain an atmosphere in a big network of underground mining, and it gets more expensive, but I guess primarily, and the one that we'll focus on today, is around the greater risk to people. But what it means for us as OEMs and suppliers is that there's a bit of a push from the industry on us, and certainly some sort of obligation for OEMs to start developing new ways for us to do work, and allow access to those difficult to reach ore bodies, make sure that we can maintain time at the face, trying to remain economical, and of course support our zero incident and injury goals, which is, any way you look at it, that's the goal for every mine out there. I guess I'd kick off with a bit of a safety share that's relevant to this application, and this is something that occurred only a few months ago up in a Queensland operation. So we had a development charge operator get struck by some material that fell from the face. Pretty standard work practices, really. Orica actually, we don't do a huge amount of development charging. We tend to leave that to the customer and then take over a lot of production, but in some instances we do. So we took over this face, handed over from the customer. In the meantime, there was, it was identified that the ground was pretty ruddy and needed to be inspected. Geotechs came down, inspected the face, decided that it needed to be meshed and bolted. At some point there's a breakdown in communication. That never occurred. And the Orica charge-up employee has gone in and started to charge the face, and there's about 800 kilograms of materials come down, and the biggest block about 250 kilos. So obviously, high consequence in the wrong circumstances there. Pretty lucky in this case where the operator was, suffered some minor injuries, but I think any of us who have been down the hole for a while have seen an incident like this. It happens all too often, and we're still seeing people get hurt, people get killed as a result of incidents like this. As we transition to bigger mines, bigger underground operations, we're seeing incidents like this occur. This is right on the extreme sort of scale of these type of events, but not all too uncommon in some operations where we're dealing with massive seismic events. And as you can imagine, if you've got a couple of operators working at the face there, digging for lifters or charging a face, the consequences are pretty severe. But it's not just those major events that we need to consider. It's often some of those innocuous events that occur similar to that safety share I just showed you, where smaller events occur, people get hurt, and over time, naturally, people suffer some serious injuries and fatalities. So A bit of a stat there from Queensland back from a couple of years ago is 54 high potential incidents and 3 fatalities from rock falls of the face over that 16-year period. And then the red box there shows where the most common occurrences are, and that's digging for lifters and charging at the face. After that period of time, the Queensland guys went on a bit of a program to start implementing face meshing, and it came in pretty heavily across the industry, but it's not everywhere still. So when we look at our current controls for how we manage geotech hazards, it can be a little bit agricultural, I guess. Manually scaling and mechanical scaling, you're addressing the hazard at a point in time, but generally you're not removing it. Particularly manual scaling has limitations in how effective it can be. The 2 other most common ways that we see that hazard being managed is by removing people from the face, so restricting access, whether it be not allowing people to go into a certain area or at all, or for a period of time until the ground's settling down. And the other common control that we see is in-cycle face support, which is you see it on most mines now, whether it be selectively or across the board. But they're time consuming, they cost money, they have a negative impact downstream, they stop us getting in and continuing to mine. And the evidence is there that they're generally at times ineffective because we still hurt people. So it's questionable as to where within that hierarchy of controls many of those controls sit. Some, we would probably place them at the lower level in terms of effectiveness. And as a result, our charge crews are exposed to many routine major hazards. We call them fatal risks, major hazards. In any language, it's the same thing. Those hazards that exist in the environment that we work in that could potentially cause a fatality. And particularly, it's not just rock falls and faces collapsing that we're exposing people to. There's a whole host of others there as well. In terms of what that means for the charge crews, I guess they're more exposed than other workers within that development cycle, particularly because they don't benefit from mechanisation and automation. So it's a pretty largely manual process, and as you see from the photos there, you're boating up primers on the shot, you're hand loading a lot of equipment, you're making manual connections, you're working at the face, you're digging lifters, you're working out of a basket, all that sort of stuff that requires you to be directly present where the hazard exists. Part of the reason that we haven't been able to get into mechanisation and automation historically is the fact that traditional initiating systems require that manual connection. So we've got leads, we've got J-clips, we've got deck cord, we've all got to connect up and all that sort of stuff to fight the face. So we've been trying to solve that for many years, and I guess you can see how old some of these are by, even the monitor in the top left picture there, it's an old CRT monitor. That's over a decade ago where we started developing some automation equipment that can identify a hole, allow you to pump product in. But what we found was the biggest constraint to doing it well and repeatably and reliably was manual connections and leads. So not only is it difficult to mechanise that process because you get tangles and that sort of stuff, it's also, has an element of risk in that you're mechanically handling a wire or a signal tube that can potentially cause an unintended initiation. So we did all sorts of projects many moons ago, and we came to the decision that it was time to abandon that sort of work and focus on removing the wires in the first place. So WebGen kicked off. So we spent a lot of years developing wireless primers. So back in 2017, we released the first version of WebGen. It allows us to safely initiate a blast through hundreds of metres of rock, water, air, whatever it might be. We can transmit a signal to a primer, and we can go from a situation like you see there, wires and leads hanging out of holes, to basically nothing. This year we'll see a new variant come out, and the one that you see on the screen there is called the Dev unit, and it's a smaller version of the wireless primer that allows us to use it in small diameter blast holes. So 34 mil in diameter, about 300 mil long, designed to be mechanically assembled, and so that you can facilitate automation of the assembly process, which allows us to store and handle segregated and then assembled just before we need to put it into a hole. So that's coming out, well, that's all been developed and we're bringing that to the market this year, but it's really been the driver for allowing us to start working on automation. And so in 2019, we partnered with Epiroc, so one of the world's largest equipment manufacturers, to develop what's now coined Avatel. And the intention was really to do what you see on the screen there, is take people away from that red zone, start by putting them in a cab, get them in a safe work area, take away some of the inconsistency with the charging process, and try and build in some automation that allows us to do a consistent job but actually get the person away from the face where the hazard exists. So it's a relatively stronger control, meaning that we can isolate workers from the hazard itself, and that allows us to reduce the, I guess, the consequence of some of those major hazards that we saw earlier. They still exist, obviously, but we have the opportunity to mitigate them largely. So this is the rig here. It's based on a jumbo sort of platform, Epiroc's M2 carrier, which sort of covers for most mining applications. But what's different about this machine, I suppose, is it doesn't drill holes, it loads them. So a few things that look different to a standard rig there is you've got an emulsion process unit at the back, carries about just under a tonne of ammonium nitrate emulsion, and that pumps through to the two booms. We've got dual carriage on this machine, which makes it a bit different to other MCUs. So we're carrying the bulk product, but we're also up in front of the, let's see if I can get this to work. Up in front of the two booms, there's a magazine up here that carries our disassembled primer. It allows us to mechanically assemble that and transport it up to the booms. Once we're up in the booms, we encode a primer, which basically gives it the delay and the capacity to fire when it receives the blast signal, and then puts it into the hole. We've also got things like string loading so that we can control the energy that we put into each hole, so that allows us to minimise the damage to the rock mass surrounding our excavation, which obviously leads to a little less work in sort of rework and scaling and all that sort of jazz, but it also helps us to maintain good rock conditions as we advance through. So built on the jumbo platform, there's a lot, we're not the only ones sort of trying to play in this space, but we've made a conscious decision to go down this road because we want to be able to produce a piece of equipment that's fit for purpose. So it fits in with the rest of the mining equipment on site. It's not a sort of retrofit to some sort of surface equipment. It's, you know, fit for purpose. It fits in with the mining cycle. It's built robust, so it's designed so that it can last in the underground environment as well. What else looks a little different? I suppose you've got some clearing mechanisms up on the boom, so it's not lost on us that, you know, there's some operational challenges with replacing a human with a machine. We've still got to access lifter holes. We've still got to move debris from the face. We've got to allow ourselves to charge all of the face. So there's a few different pieces there that allow us to cover off, I guess, you know, any tasks that a human would normally do. And the operator never leaves the cab to do so. So a few happy snaps, if I go back, a few little happy snaps there, so you can see the top right there, that's our emulsion body. Like I say, carries about a tonne of emulsion. Our segregated, what we call a day box or magazine. So this front partition here carries the boosters, and in the back you carry what's called the DRX, which is a receiver and a detonator. And then it's all shrouded in and it sits between the booms. There's a few different configurations of how we remove debris. That's what we call a bit of a street sweeper type scenario, which is far more effective than I thought it would be based on what we've done. But the brains of everything is the control system. It allows us to control all of the charging process, but also talk to the rig. So it's fully integrated, which means that we can pick up for example, an as-drilled data file. We can plug it into the rig. We automate the blast plan. It allows us to navigate to a hole and allocate the right energy and delay to that hole. And really the operator's in there moving the booms around and they're confirming that everything's correct before they press start. So it does take a bit of the decision making away from the operator, which allows us to have a bit more consistency in the execution of the blast. Taking that configuration and maybe putting it into an operational context, we're trying to sort of have a bit of a step change here between, you know, what we're requiring an operator to do and what we can do now from the cab. Standard practice for a dev charge at the moment is we head up to the face, we do some scaling, we get in with the get lifters or we access the lifters that the jumbo operator has installed. We go and jump in the basket, charge top down generally. That picture there is obviously not top down. And I guess one of the reasons for that is different operations prioritise the snap, slap or shoot type risk versus your hazard of getting snotted by a rock a little differently. So that's actually a mine over in Europe that I was at recently that charged bottom up because they're concerned about material falling from the face. Yet they still don't go and support the face, so it's an interesting one there. But and then we go about charging from the floor to do the bottom of the half of the face, and that's generally where we see people get hurt. Put people in a machine, we don't have to scale, we don't have to install lifted tube, we don't have to have people out there exposing it, we don't have any of that risk of snap, slap or shoot, and we're reduced risk of misfire because we're seeing no, I guess, damage to connections between the det cord and the det, and there's no restrictions on how we can charge a face. We can charge top down, bottom up, left, right, whatever you need, because there's no wires and that risk doesn't exist anymore. Similarly, when we talk about explosives handling, it's different now. So normally we generally bait up our primers at the face out of the basket or at the machine and take them up. We're in the basket managing charge hoses, pumps, buttons, signal tubes, connections, all that sort of stuff. And then we're relying on people again to do the right job in terms of being consistent in the way that they charge a face, which means that handling practices are different, so the risk of an adverse blast exists because people tend to do things differently, and then that compliance piece is difficult as well. When we go and mechanise and start automating, for Avatel, for example, we're not baiting up primers and taking them up to the face. Everything happens on the machine, and nothing happens until it's ready to go into a hole. So you've got disassembled, segregated explosives right until the last minute where it's required to go into a blast hole. We don't have that risk of damaged connections between the det cord and the det, so less risk of misfire in that respect. Everything's consistent. It's a press button. The machine controls all of the application of the explosives in the hole. Anything from making sure that the primer has the correct delay through to making sure that the right energy is allocated to the hole. Everything's digitally audited, or auditable. So we output a file at the back end that tells you exactly what has gone into every hole, what inventory's been used. And then the system itself, the WebGen system, is still 3 rated. So there's I think the stat is something 1 in 10 billion chance of an unintended initiation, which means that the firing system itself is incredibly safe. There's a lot of layers of security and control to make sure that you can only fire that particular blast that you intend to. But naturally, there's some new hazards to consider as we go into wireless primers as well. So that's, I guess, the system. Where are we up to? We're in Europe. We've got 2 rigs running around at the moment. So over in Europe at the moment, we've been running through our V&V program for the last 3.5 years. So it's been a big effort, but we're underground now. We've been spending a fair bit of time at the Nacka mine just out right in the centre of Stockholm, actually, which is an epi-rock facility. We've been running the rig through its paces over there, and then we're next week kicking off another trial at a site up in the north of Finland, up in Lapland. So we'll spend the next few months doing those trials, and then really sort of working through that reliability and repeatability piece. We're pretty confident now that the machine functions as it's intended to. We're charging 80 hole faces in about 2 hours, which is about where we want to end up. And the next step really is to prove that mechanical reliability piece. But in parallel, we've got a rig over here in Australia, so actually kicking off wet commissioning today in our Kurri Kurri facility. So we built this unit in parallel so that we could, I guess, minimise the time between going through all this prototype work and getting something out in the field. So that machine's sitting there now ready to go, and before the end of the year we're heading out to Cadia. So the guys at Newcrest have been fantastic in supporting this program. They've long had a history of innovation and bringing new technology, and particularly in the blasting space, to facilitate safe work. So we're really happy to have those guys on board, and we'll be out there before the end of the year. And that's largely it. I mean, in terms of what does this mean for implementing a machine like this in Australia, it's basically designed to be as safe or safer than any other MCU that Orica has out in the field. So it means that while it is a global product, which means that we have to have a base to work off that allows for regional modification, when we bring it to Oz, we have to do some mods to make sure that it meets our local legislation. So that's making sure that we're compliant with the ACID code, and also making sure that we're compliant with the AS2187 pieces, and it'll all be it goes through Orica's internal auditing process to ensure that we meet our own satisfaction of meeting those codes along with their own. And then, of course, the MDG 15 and site compliance piece gets done as well. So there's some upgrades done to the base machine that gets happened and that gets brought across to Oz, and away we go. So that's UG 7000. That's the first rig to hit its straps underground here in Oz, which is really exciting for us. And I guess the next 6 months in particular is really important for us in making sure that we can demonstrate reliability out of Cadia and also generate some value for the guys at the same time. I guess that's it. The message really for me is we want to see mechanisation and automation change the way we do work, and I think there's a real opportunity for it. This might not be the end solution, but it's certainly the way the industry's heading. We need to take people away from hazardous environments and at least begin by protecting them by putting them in a cabin, getting them away from the face in this case. For us, this is probably the most heavy undertaking we've taken in terms of automation and mechanisation. Solving development first was pretty bold, and I think it's probably the application for automated explosives that is the most challenging to solve. Everything else is pretty straightforward after we get through here. So this is the first step, and we'd like to see ourselves do more of it. But yeah, I think I don't have too much more. I think that's everything. I'll leave it there. Yeah, thanks for having me.